some point. So we want to talk about the kernel of a linear map. And I'm pretty sure that if we want to talk about a linear map, so this is just a map between spaces. So we have two vector spaces, let's call them. So we have a vector space, let's call it V, and we have a vector space. Let's call it W. And we have some kind of mapping between these two vector spaces. So what should we call it? Let's call it phi, since that's what we're going to use in the question. So we have these two vector spaces. We have some kind of map that takes vectors from vector space V into vector space W. And I'm pretty sure the kernel of a linear map is all of the vectors that get sent to the zero vector inside of set W. So I'm pretty sure that the kernel of our linear map should be the set of vectors, should be all of the V's in V, such that phi of V is equal to the zero vector, and this zero vector is in the vector space W. So I'm pretty sure that's how we want to think about the kernel map, or the kernel of our linear map. So like this, I think, is the definition. Right? It's defined as the set of vectors that get sent to the zero vector. Plaisant, I see. Okay, so Plaisant has got a good idea. Plaisant says, hey, if we have a vector and we try to add to it the transpose, it doesn't make any sense. Right, okay. So A has to be an n by n matrix then. So it can only be for square matrices. So we have to add A and its transpose. I got you. So A has to be an n by n matrix just by the way this is set up and working. Okay, so let's move this up. That's going to be our definition of our kernel. And then the next thing we want to do is we want to figure out what the kernel is for this specific example. So let's try to calculate kernel of phi for our example. So what do we know? We know that A must be an n by n matrix, since we are adding A and its transpose. Right? So if A was m by n, for example, I wouldn't be able to transpose that and add these things together. It's just not defined nicely. So what do we actually want to do? We actually want to set this equal to the zero matrix, don't we? Okay, so I think we have to set A plus A transpose equal to the zero matrix, right? So we see that A has to be equal to the negative of its transpose. So they're not symmetric, but they have to be anti-symmetric. So wouldn't they have to look something like this? I mean, if I just do a 2 by 2, like A, B, C, and D, then this is saying that my transpose, A, D, B, and C, these have to be negatives of each other. So that gives me some information about B and C, I suppose, right? And this must be multiplied by -1. Do these matrices exist? I feel like these matrices are just very odd looking. Oh. So the main so you're saying that A would have to equal negative A, that D would have to equal negative D, and that B would have to equal negative C, and that C would have to equal negative B. So this basically tells us that A and D have to be equal to 0. And these other two tell us that these numbers have to be opposites of each other. Okay. Yeah. I can see that. So the actual 2 by 2 matrices that would work would look like this. Right. Okay, because when I take the transpose, it's actually -1 times the original thing. Oh, okay. And this is a basis, essentially, right? So this is going to be a basis for the 2x2 case for the kernel. This will be our basis. That makes sense. Okay. I think we're rolling with this. Right? This is the set of skew symmetric matrices. Any matrix that satisfies that particular property should be a part of the kernel. And so we don't really have to go into determinants, I don't think. I don't think that was really helpful. So what do we say? We say that the kernel of our transformation should be the set of A's. And these are n by n matrices such that A is equal to A negative A transpose.